Hello, can you guys hear me okay? All right, thanks, Steph. So throughout the talk so far, you've probably heard open source models a bunch of times, quality a bunch of times, but a big part of taking models to production is actually making sure that you have highly reliable inference and also very high throughput, especially true for real-time applications, so on and so forth. And so the goal of my talk today is to walk you through the not so nice parts of open source and then how we can actually incrementally fix them. So yeah, that's the high level sort of picture, sort of goal for this talk. So some of the challenges, if you've used open source LLMs, you've probably noticed one of two things, or both. The first is that throughput is often not very high. So compared to GPT-4, GPT-4 Turbo, you're going to see a 2x or 3x number of tokens per second. However, for a lot of real-time applications like chat, summarization, code generation for in-house code, it may not be fast enough, right? So that's one problem. And the second is that open source models out of the box, as Piero showed you earlier, they don't do so well on highly domain-specific or tasks or very curated tasks, right? This is an example of Con LLPP. It's a popular benchmark data set. It's named entity recognition. And what you'll see is that we got really poor accuracy and also fairly low root score. It's not the best metric, but hopefully it'll make sense as we go through this talk. So the question really is, well, what can we do about both speed and quality? So there are actually many methods to improve open source model throughput, right? Like here's an example where we did some special things. And you can go from 70 to 93 or 71 to 117, just depends. And I'll talk about it through the rest of the talk. However, the problem is that you're just improving speed, but your quality is still poor, right? On the other hand, we know from Vlad and Piero that LoRa fine-tuning can increase base model performance pretty significantly, right? So this is the same models. Post fine-tuning, you'll see it's like nearly 15x increase in accuracy and almost 2x increase in rouge. But the problem with somewhat of a problem with LoRa fine-tuning is that because we're injecting new modules into your base model, we're essentially increasing the size of the model fractionally, and it also means there's more multiplication. So you're going to partially impact throughput. And the real question is well, what can we do to solve both of these problems? Because that is what we want to do. And normally, there's a trade-off, right? You either, as I just showed you, but what we're going to try and do is solve for both. We'll start with throughput, and then we'll work our way into quality and see what we can do. So before we jump into throughput, I think for those, just as a quick refresher, it's important to understand why LLMs are actually slow, right? There's a pretty fundamental reason, starting with autoregressive language models. I'm not sure how well you can see this all the way at the back, but the main idea I want to demonstrate here is that you have a set of tokens. These are essentially words that get converted to integers. You pass them through the embedding layer, which converts it to some sort of vector. You pass it through the rest of your transformer layers, and the output of that gets passed to something called the language model head, or the LM head, and you predict, let's say, the next token. So this is traditionally how it works. Just to put that in the flesh a bit more, here's an example. Let's imagine it's a GPT-2. You've got the quick brown fox as input. So these get mapped to tokens, which then get passed into the model. And the model produces something called logits, which are basically these unnormalized log values. And what most people do is they apply a softmax function to turn these into probability distributions. And then you can just pick the token with the highest probability and map it back to a word. So in this case, we maybe predicted token number 11687, and that maps to jumped. So what happens next? The way this usually works in LLM inference is that we then take this word, append it to our initial input sequence, and then pass it through the model again. So we could take this whole new sequence, pass it through our entire big model, get logits, do some sampling, get a token, and we repeat this over and over and over until the model usually produces something called a stop token. And when we see a stop token, we break out of a loop and we return the sequence. If you've noticed, there's a very interesting trend in the way LLMs work, right? They do a token by token generation. We're having to append it to our initial sequence and then pass it through the full model again. And what this means for response time, if you've seen this in the way ChatGPT streams tokens or open source models, is that there's a linear relationship between the number of tokens generated and the time it takes, because it uniformly takes the same amount of time to generate each token. So you're going to scale your tokens generated by the time, or the time by the number of tokens you generate, and that's really like not a sustainable way to do inference. So the question is, well, this is an entire model. What can we do about it? And some very clever people came up with this idea of speculative decoding. And what it is a very fundamental change in the way we think about autoregressive LLMs. The main idea behind it is that instead of just predicting the next token every single time, which is expensive to do because we have to pass the full sequence through the model, what if you could actually guess not just the next token, but n tokens ahead of it? So not just the second token, the third token, the fourth token that might come after. The biggest cost in LLM inference that I wanted to highlight from the previous demonstration is passing all of these inputs through your big model. And this scales with the size of the model. So if while paying the cost of doing a single forward pass, we can generate many tokens and then verify that they are correct, we're actually going to cut down our time proportionally. And so this idea of speculative decoding has typically two steps. There's a draft step, where we actually predict k future tokens, and then a verify step, because we still want to make sure that our guesses are actually correct, so the LLM output is correct. And very simply put, if we can make this process very cheap and we make our guesses correct, then we're going to see significant speed-ups in generation. So the simplest idea that one can use, and people used this a lot last year, is this idea called assisted generation. If you've seen, let's say the Llama family Meta came up with the Llama family of models, and there was the 7 billion parameter model, 8, 13, 70. The idea of assisted generation is very simple. You have a large model, let's say Llama 70 billion, and an assistant model, or called, let's say, Llama 7 billion. And the idea is that we want the assistant model to do the guesswork. So the assistant model takes in the input and produces up to k future tokens as guesses. And then we pass that to the big model to actually verify that these are correct. So we're going to take the original input, the guesses, pass it to the big model, and then see what the big model would have predicted for each of those tokens in those exact positions. And it's very simple, right? So in this case, our small assistant model produced jumps over the tiny dog. And when we passed it to the big model to verify, we saw that we were able to correctly guess jumps over the, but then we predicted tiny and then dog. And while dog is correct, since tiny is wrong, we have to discard everything that comes after the. And so we just keep those tokens there. And this is like a simple idea, and this only works. There's one very important thing. The reason I use Llama 70 and Llama 7 is that both of those are trained on the same pre-training data, just different volumes of it. So that means that the underlying distributions are similar, which means that your guesses have high likelihoods of being right. However, there are actually many problems with assisted generation. The first is that you actually now have to pay the cost of two models in production, right? So you've got the big model, you've got this draft model. The second is, the distribution should be the same. So what this really means is, let's say you were doing full fine-tuning and you fine-tuned your big model, you also have to fine-tune the smaller draft model on the same data because the distributions need to stay in line. And the third is that usually you're going to put these on separate GPUs. So you need a fast interconnect or something in between so that the small model and the big model can communicate. So you can pass tokens across, send logics back, so on and so forth. And this is actually quite slow in practice. So the real question is, can we do better than this? Do we really need a second model? And can we just do it in one model in a way that is parameter efficient? And so that's where the second idea comes in, which is actually you can fine-tune for speed. This is through a method called Medusa. It's a very popular paper that came out, I think, several months ago. And the basic idea with Medusa is that, again, I'm not sure how well everyone can see it, but the idea is very simple. So you've got your same inputs that go into the model. You've got the model as it was. The difference is that in addition, towards the end, the last hidden state is not only passed in through the original language model head, but it's also passed through a set of linear layers, and then a copy of the LLM head that is fine-tuned. And so the idea is that you see Medusa 0, Medusa 1, and Medusa 2. Medusa 0 is predicting the n plus 1th token, and Medusa 1 is predicting the n plus 2th token using the last hidden state from the original transformer model. And this actually works really well in practice. And I'll show you some results in a moment. The question is, how does one train such a Medusa, right? And there's a very simple sort of general framework to think about. Let's say you have a chat data set. What you can do is take your chat data set, take all the user queries, pass it through the model, and generate the assistant outputs, which is what the model would generate if you were to chat with it. And then you can actually fine-tune the model. So this gives you a data set, right? And then you can actually fine-tune this model on this data set that you've produced. But you only train the Medusa layers in your model. And you go through the same fine-tuning process that Pierre described prior, and you're going to get these trained Medusa heads that you can use. And in terms of performance, it's quite cool, right? So if you train, let's say, so let me explain some terminology here. You're going to see this term called general Medusa. And it's just the idea that if I take a general purpose chat data set, train my Medusa to speculate, right? And then I serve it, even on task-specific data sets, there's like a pretty significant lift in throughput. So on the left side, about 30%, on the right side, maybe about 50%, which is pretty significant, assuming you have enough data to fine-tune, which is really important. The second is if I actually now take, let's say, Vlad's exact data set, which was this sort of query to classification, and I was to fine-tune that model. So on fine-tune Medusa on a very specific data set, you can actually get more than 2x throughput improvement. So the same data set the same model that was giving you 70 tokens per second is now giving you 147 or 130, depends on your task type. But the question really is, well, this is good. We're getting much faster throughput. But remember, from the earliest chart I had, the quality is still terrible. So we need to account for that. And I won't spend much time on this, but LoRa is definitely like the most parameter efficient way to get high quality. And you can do it fairly cheaply without a lot of effort or a lot of data. And just maybe like a different view of the data Pierre presented earlier. This chart, for those who can't see, is a list of models from left to right. Some closed source, some open source. And what you'll see is that all of these models do significantly better post fine-tuning compared to closed source models. So we know LoRa works really well, either matches closed source or beats closed source. But how do we actually fuse this idea of Medusa training with this idea of LoRa training, but then also make it so parameter efficient that you still don't need a lot of data to get the best of both? And that is what we spend a lot of time building at Predibase. We call it the Turbo LoRa adapter. And the idea is very simple. So this is the same Medusa chart from before, but with two big changes. The first is that in the transformer block, so the Q, the K, and the V projections, we insert LoRa weights that we train. And remember, we're doing LoRa because we want it to be really good at a task. And the second thing we're doing is we've actually done two big changes to the Medusa architecture. The first, to make it parameter efficient. The first is that we're not going to use separate LM heads. Those are really, really expensive to compute and also to train. And the second is we got rid of all of the the MLP layers before the Medusa heads. And so what this means is compared to the original Medusa, you've actually shrunk your trainable space by about another 100x, or 2 orders of magnitude. And what it also means is that with like 2,000 to 5,000 data points, you can get nearly like 95% accuracy on your Medusa guesses, which is exactly what you'd want if you want to push throughput. And just to explain, like maybe at a slightly deeper level, like what this joint training looks like, this is the loss function. I'm calling it the LoRa plus Medusa loss, and it's some weighted average of training for LoRa and training for Medusa. You remember, you have to balance, what we learned is that you have to balance task-specific learning, so the actual knowledge injection, with throughput, because otherwise your outputs collapse. And here's some benchmark numbers. Again, don't know how well everyone can see it at the back, but when we did base model with LoRa, we were getting about 52 to 51 tokens per second, both on the con NLPP dataset, which is named entity recognition, and magic coder, which is code. But when we do base model plus Turbo LoRa on the exact same hardware with the same eval set, everything constant, we saw over almost a 3.5x improvement throughput for the con NLPP dataset, and about almost a 3x throughput improvement for Magic Coder. So pretty significant. And the other thing is that because we made it, one of the reasons we wanted to make it so parameter efficient is for two reasons. One, we want to be able to hot swap these kinds of adapters into LoRax, the engine that Pierre was talking about earlier. And the second is that the more weights we add, the worse your time to first token gets, and that doesn't really work well for a lot of production applications. So keeping both those in mind, we built it this way. And in terms of quality, what you'll find very surprising, and as did we, is that actually the model performance gets even better with the Turbo LoRA adapters compared to the LoRa adapters. So you're not just getting an improvement in throughput, you're also getting much higher quality. Our con NLPP accuracy went up from 0.92% to 97%. Magic Coder Rouge went up to like 0.517, which is pretty high, like big overlap in output. So you get a lot of benefits of both by training this way, both speed and without sacrificing any accuracy or time to first token. Here's another view. So remember, we started with the base model. Then we said base model plus LoRa is good for quality, but gets worse in performance in terms of throughput. But once we fine-tune with the Turbo LoRa adapter, we actually go back up significantly on throughput without giving up quality. And what's cool about Turbo LoRa, and I think this is actually very important thing to note, is that it's hardware agnostic. So as long as you're using GPUs that have enough tensor cores, which is usually any GPU out there that's not a T4 GPU, you'll see that on average across all hardware and across a variety of tasks, we saw at least a 2x improvement in throughput, and in many cases up to 3x. And also, one of the fun things that we've been doing is playing around with FP8, which I don't know if you guys are familiar, but it's a new data type or data format. Don't have the numbers here, but in our early benchmarking internally, we're seeing like a 4.5x improvement in throughput. So that's like over 200, 225, 250 tokens on the same piece of hardware. And this is on the L4, so these are actually like not even the best GPUs. There's L40s, there's H100s that will show you even higher throughput if you were to go through this method. So with that, just want to wrap up. We built this exclusively into Predibase for various reasons. Just it's much easier to own like an end-to-end training and serving story. But if you use the platform, we support many different data integrations from S3 to Databricks. You can customize. We support like over 100 open source models that you can train everything to the latest. We try and get every model in within a day. We're really good. At least one of the things we try to do is make this a place where people can collaborate. So you can version different models, which is a big pain point if you're training, compare, iterate very easily, train many jobs in parallel, which is pretty nice. And finally, LoRax actually supports Turbo LoRa adapters, which are specially trained in-house. So you can serve these cost-effectively at scale. Maybe one thing that would help bring home this point of why throughput matters is just faster throughput means lower cost. You need fewer replicas to serve your load. And that's a pretty underrated but very important aspect of taking LLMs to production. Cool. And yeah, that's me.
Thank you very much, Arnav. I feel like I always learn something listening to that talk over and over. Cool. Any questions? I see one right over here. Let me go get you the mic.
Hi.
If you could just introduce your name and role.
Yes. Tanay, Principal Data Engineer. So no quantization, experimentation to reduce the model size?
So a lot of the models that we train, are you saying for training or for inference or both? So the ones that we've played around with are a lot of 4-bit quantizations, which are a bit lossy, and also slower because they're not as efficient in terms of implementation. And FP8, which is the one we're most excited about today. The really cool thing that, we're actually going to probably announce this in a week or two, but the really cool thing is that you can fine-tune on FP16, serve on FP8, and you don't lose any performance. So yeah, we do it all with FP8. We think it's pretty big, and we're going to keep exploring on 4-bit quantization as well.
Cool. Time for one more question if anyone has one. Yeah, let's go right over here.
Thank you. Thank you for the presentation. I'm Daniel, Engineering Manager. I had a question as to when you're guessing what the model is going to predict, and maybe you get better accuracy, How do you kind of measure the significance of that metric when regarding, for example, if in Vlad's case or in the medical field, the difference between, say, 10 words, you get them 9 right, but does and doesn't, you get wrong. So this person has cancer, does not have cancer, right? Can you speak to that? And the follow-up I want to ask, can you talk a little bit of your thoughts of why the performance also increases with this?
Both are great questions. So think maybe have misspoken, but it's a great question that you have. So the cool thing about the speculative decoding is that you're guaranteed that the outputs are exactly the same. You can never produce something from speculative decoding that you wouldn't normally produce by the LLM if you were to just do it normally. The only difference is in speed. So the whole idea is that you want to speculate on these tokens, but you want to verify them right after. But you're trying to make the cost of generating these tokens ahead very cheap. So you actually, like, if it has cancer, it will produce has cancer, but it won't guess something else if it was going to originally guess that. Now, the way to think about improvement maybe is, let's say you have 3 of these speculators, or we call them turbos, right? So what we do internally while training is that we measure something called top 1 accuracy, which is given the whole spread of tokens, did you predict the right token next? And only one token. Like, you need to get the right token or it doesn't matter. And usually what we see is, given sufficient data, you can get like 90% accuracy on each of these turbos. But what this means is very interesting. It doesn't mean that you're going to see 90% of the times all guesses be correct. There is, because of the way LLMs work, this like AND property. And ANDing means we need to multiply the probability distribution. So if Turbo 0 gives you 90% and Turbo 1 gives you 90%, it means that 80% of cases you will get both guesses right on average. To your second question on why performance improves, it's a great question. So as it turns out, because we're training a new set of projections, which are the turbo layers, we're adding in new parameters into the model. And given enough data, they actually tend to also learn some task-specific characteristics. You're basically increasing the model capacity to learn. Like, maybe the LoRAs were not sufficient, and there was room to improve. And this indirectly is learning both task-specific characteristics, but also the speculation part. And I think that's the phenomenon. That's the running theory I have on why it improves. Hopefully that's useful.
Perfect. Thank you very much, Arnav, for that.